Curve of constant width. In geometry, a curve of constant width is a simple closed curve in the plane whose width, the distance between parallel supporting lines, is the same in all directions. The shape bounded by a curve of constant width is a body of constant width or an orbiform, the name given to these shapes by Leonhard Euler. Standard examples are the circle and the Reuleaux triangle. These curves can also be constructed using circular arcs centered at crossings of an arrangement of lines, as the involutes of certain curves, or by intersecting circles centered on a partial curve. Every body of constant width is a convex set, its boundary crossed at most twice by any line, and if the line crosses perpendicularly, it does so at both crossings, separated by the width. By Barbier's theorem, the body's perimeter is exactly p times its width, but its area depends on its shape, with the Reuleaux triangle having the smallest possible area for its width and the circle the largest. Every superset of a body of constant width includes pairs of points that are farther apart. Although the Reuleaux triangle is not smooth, curves of constant width can always be approximated arbitrarily closely by smooth curves of the same constant width. Cylinders with constant width cross-section can be used as rollers to support a level surface. Another application of curves of constant width is for coinage shapes, where regular Reuleaux polygons are a common choice. The possibility that curves other than circles can have constant width makes it more complicated to check the roundness of an object. Curves of constant width have been generalized in several ways to higher dimensions and to non-Euclidean geometry. Definitions. Width and constant width are defined in terms of the supporting lines of curves. These are lines that touch a curve without crossing it. Every compact curve in the plane has two supporting lines in any given direction, with the curve sandwiched between them. The Euclidean distance between these two lines is the width of the curve in that direction, and a curve has constant width if this distance is the same for all directions of lines. The width of a bounded convex set can be defined in the same way as for curves, by the distance between pairs of parallel lines that touch the set without crossing it, and a convex set is a body of constant width when this distance is non-zero and does not depend on the direction of the lines. Every body of constant width has a curve of constant width as its boundary, and every curve of constant width has a body of constant width as its convex hull. Another equivalent way to define the width of a compact curve or of a convex set is by looking at its orthogonal projection onto a line. In both cases, the projection is a line segment whose length equals the distance between support lines that are perpendicular to the line. So a curve or a convex set has constant width when all of its orthogonal projections have the same length. Examples. Circles have constant width equal to their diameter. On the other hand, squares do not. Supporting lines parallel to two opposite sides of the square are closer together than supporting lines parallel to a diagonal. More generally, no polygon can have constant width. However, there are other shapes of constant width. A standard example is the Reuleaux triangle, the intersection of three circles, each centered where the other two circles cross. Its boundary curve consists of three arcs of these circles, meeting at 120 angles, so it is not smooth. Other curves of constant width can be smooth but non-circular, not even having any circular arcs in their boundary. For instance, the zero set of the polynomial below forms a non-circular smooth algebraic curve of constant width. Its degree 8 is the minimum possible degree for a polynomial that defines a non-circular curve of constant width. Constructions. Properties. Applications. Because of the ability of curves of constant width to roll between parallel lines, any cylinder with a curve of constant width as its cross-section can act as a roller, supporting a level plane and keeping it flat as it rolls along any level surface. However, the center of the roller moves up and down as it rolls, so this construction would not work for wheels in this shape attached to fixed axles. Some coinage shapes are non-circular bodies of constant width. For instance, the British 20-type and 5th-type coins are Reuleaux heptagons, and the Canadian loonie is a Reuleaux 11-gon. These shapes allow automated coin machines to recognize these coins from their widths, regardless of the orientation of the coin in the machine. On the other hand, testing the width is inadequate to determine the roundness of an object. Overlooking this fact may have played a role in the Space Shuttle Challenger disaster, as the roundness of sections of the rocket in that launch was tested only by measuring widths, and off-round shapes may cause unusually high stresses that could have been one of the factors causing the disaster. Generalizations. The curves of constant width can be generalized to certain non-convex curves, the curves that have two tangent lines in each direction, with the same separation between these two lines regardless of their direction. As a limiting case, the projective hedgehog's curves with one tangent line in each direction have also been called curves of zero width. One way to generalize these concepts to three dimensions is through the surfaces of constant width. The three-dimensional analog of a Reuleaux triangle, the Reuleaux tetrahedron, does not have constant width, but minor changes to it produce the Meissner bodies, which do. The curves of constant width may also be generalized to the bodies of constant brightness, three-dimensional shapes whose two-dimensional projections all have equal area. These shapes obey a generalization of Barbier's theorem. A different class of three-dimensional generalizations. The space curves of constant width are defined by the properties that each plane, curves, and bodies of constant width have also been studied in non-Euclidean geometry and for non-Euclidean normed vector spaces.